All right. Okay, so I'm thinking, I'm kind of thinking out loud right now. I'm trying to figure out what we should do for kind of the plan. Okay, so this is the plan for the rest of the course. And so, okay, so today we'll see how far I get in lecture. This is why the plan's a little bit up in the air. So this is the plan. Today I'm going to cover the EM algorithm for sure, and then plus maybe PCA. I don't know if I can cover both in one day. So then, and then next week, which is technically week 6, okay. Monday is technically a holiday. Monday is Labor Day holiday. And I was debating whether I want to do a lecture or not on that day. And then next week, so we have Monday, and then the final exam is scheduled for Friday. So this is what I'm thinking. Okay, I'm thinking I'm going to I will do a live lecture on Monday, but it will be recorded. Also recorded. And if you want to attend live, you can attend live. But if you want to take Monday off, you can take Monday off and just watch it recorded. And I think what I'll do is I'll extend the due date for the viewing quiz to like Thursday. And then I'll kind of also, and so during Monday, I will probably wrap up PCA, and also go over topics for the final exam. That'll give you, rather than putting it on Wednesday and then you have only like a day and a half to absorb everything. So this is what I'm thinking. I'll put the lecture on Monday, and then on Wednesday we'll take our holiday there. So we'll say no class on Wednesday. Is that okay? And then yeah, so so I'll give you kind of the list of topics that will be covered on the final exam. All right, and then final exam will be on Friday, and we'll have the 2 times as well. So 1 p.m. and 10 p.m. Okay. If the PCA is covered on next Monday, well, yes, PCA will be on the final exam. Yeah. So that's why I want to start covering it. We'll see if I can start covering it today, and then I'm gonna. That's why I want to wrap it up on Monday rather than wrapping it up on Wednesday. Okay, because if I do it on Wednesday, then you really only have a very short amount of time to kind of absorb PCA. So so I think today we'll do EM algorithm plus PCA, or at least the start of PCA part 1. And then Monday I'll wrap up PCA. Okay. Are there any topics that we will not have time to cover during the course? So, so one part that we didn't really get to cover was like Fisher information. So one topic that I had to abbreviate was maximum likelihood estimation of the parameters. So we did cover the MLE approach to like linear regression. Like maybe in a 10-week course, I would have spent a little bit longer time. We would have covered the maximum likelihood estimate of the variance in linear regression, and along with Fisher information. And I think that topic will, would have been maybe a lecture in there, and that gets a little bit cut a little bit short. So I hope you're not too brokenhearted about that. It is there. You can read about it in, I think, chapter 2 in the textbook. Yeah, I can throw up those slides, but yeah, I guess I'll make it clear that they are not going to be on the final. Is it the same thing for MLE that we learned in 100C? Probably very closely related, very closely related. I don't know what exactly is covered in 100C. I've never taught 100C, and I haven't taken it either, so I don't know the exact list of topics. There's definitely a lot of overlap between the different stats classes, right? So, you know, but we take different approaches. So this class is a little bit more of a computational emphasis on coding and you know, algorithm writing for a lot of the similar topics. You know, there's a lot of kind of overlap between this class and 101C. I think 101C you do things like, I think you do KNN and stuff. I'm not 100% sure, but you don't. I'm pretty sure you don't write the algorithms yourself in that class, whereas in this class, that's kind of what I make you guys do. Are there any questions? Does this sound reasonable for what the plan is next week? So on Monday, it's a holiday, but I will do my lecture on Monday, and then I'll have no class on Wednesday. So you still get the day off, and then the final will be on Friday. And that way, okay, yeah. So you'll have to. I'll have to remember this. Okay, so then I'll do office hours on Thursday. Thursday at 1 p.m. will be office hours. I gotta. You might have to remind me in case I forget. So I'll put that in my calendar. Okay. And Friday, yeah, office hours on Friday. Well, Wednesday, so I'm not planning on doing anything on Wednesday, and I don't really have a review session. So on Monday, when I go over the topics for the final, like I think I'm fairly generous. I'll be fairly generous in terms of like what kind of problems you can expect without writing out the actual problem, you know, like kind of like the midterm. I think I gave a fairly generous description of what you could expect on the midterm, and what showed up on the midterm was, I think, matched the description that I gave. And so it will be kind of similar like that on Monday. I'll give a description of what you can expect to see on the final, and what you see on the final should match that description closely. And that will be kind of the closest thing I have to a review, because and then, you know, the review will be what you study as you go over those topics. And yes, homework 6 will be due next Friday. I know it feels like you don't have a lot of time to go to finish homework 6, but I think it's plenty of time. Homework 6, I don't think is I'll give you like I think it's a reasonable amount of time to complete homework 6. So, all right. Questions? So this is kind of, I'll put this up on CCLE. Will the final be cumulative? Not really. Definitely stuff. I won't really test you on the same kind of stuff from before the midterm. So I'll go over the list of topics here. Okay, I'll go over the list of topics on Monday. Homework 6, I'll get that posted before Monday. So probably like tomorrow. You can expect to see homework 6 up by tomorrow. Okay, so all right, and that is that. Okay, I guess we'll so I will cover the EM, and then we'll see. I'll get started on PCA. This is labeled week 6 Monday, but probably this will end up being week 5 Wednesday part 2. All right. Oh, and then I hope you've enjoyed the course. And I think course evaluations are now open. So I greatly appreciate you guys taking the time to respond. You know, filling out those evaluations. I hope you feel like you've been learning stuff. You know, despite kind of the change in format, you know, I know doing things online isn't the most ideal circumstance, but given what we've had, I hope you've enjoyed it. And yeah, please leave a review in for your course evaluations. All right. Okay, so so we will cover the EM algorithm for Gaussian mixtures. So the EM algorithm is known as the expectation maximization algorithm. It's an iterative algorithm that goes between two steps. One is called the E step and the other is called the M step. And the E step is the expectation step. The M step is the maximization step. And it can technically be applied to many different situations. But so in our class, we will look at the EM algorithm for Gaussian mixtures, just because we've already seen Gaussian mixtures when we did the Bayes classifier and naive Bayes classifier. So we're already a little bit familiar with the concept of Gaussian mixtures, and then applying the EM algorithm is I think a good application of the EM algorithm and can form a good starting point. And then if you decide to pursue statistics further, you know, you will encounter the EM algorithm almost surely in the future, and you'll probably encounter like a more generalized version of the EM algorithm. But hopefully what you've kind of learned here on Gaussian mixtures, you can then associate the ideas further here. All right. So the EM algorithm for Gaussian mixtures is kind of is another unsupervised learning method. So unsupervised, again, means we do not know any kind of class labels. There's no target values. All you have is just a bunch of data, and you are trying to group observations together. So you're trying to find structure within the unlabeled data. And when we are doing the EM algorithm for a Gaussian mixture, what we're going to look for is we're looking for kind of clusters, but in the form of Gaussian distributions. All right. So first I'm going to start off with a mixture of Gaussians. All right. So we're going to have a mixture of 3 multivariate Gaussian or multivariate normal distributions, and they're going to come from some kind of data generating process. All right. And so here I'm going to have three Gaussian distributions, and they will be generated with, or their mixture components, okay, their mixture quantities is given by this vector 0.5, 0.3, 0.2, okay? So values will come from the first component with a 50% probability. Values will come from the second component with a 30% probability, and values will come from the third component with a 20% probability, all right? So basically, the process for generating our total data is randomly select the value 1, 2, or 3 based on these probabilities. So we're gonna say, you know, this is, have you guys learned the multinomial distribution? Multinomial? Yeah, no, maybe. It's kind of like the binomial, except you can have different outcomes. So you can think of it as spinning a wheel, or spinning a, I don't know, like one of those arrows on like Twister or something. Okay, you spin the thing, and then wherever it lands, that's what you select. And so you can think of separating the circle into, you know, half of it is 1, and then 30% is 2, and then 20% is 3. Okay, and then you spin the wheel, and then, or you spin the spinner, and then so there's a 50% probability it ends up, you know, the spinner points at 1, you know, 30% probability that it ends up in zone, whatever, zone 2, and a 20% probability that ends up in zone 3 or something. So that's kind of the multinomial distribution. In the multinomial, you're just asking for the total count, but here this is just a multinomial with a count of 1. So we're gonna generate one of these things, and then once you've generated which cluster it's coming from, then you generate a value using the multivariate Gaussian distribution. So here we can just do, in R, we can just say, give me a random multivariate normal value. So you can use RMV norm or RMVT norm. I forget what it is. Okay, random multivariate normal value. And so the first component will be centered at 0, 0, and it has this variance matrix. Okay, so 9, 0, 0, 9. The second component will be centered at 4, 4, and we'll have this variance matrix, okay, 1.9.91. Okay, so there's high covariance between x1 and x2. And then component 3 will be centered at -4, -4, and it has this variance matrix, 2, -1, -1, 2. All right. And so mathematically, we can represent the total mixture model as this, okay? It is the sum of alpha sub k, multiplied by p sub k, okay? It's the sum of all, so there's k components. In our case, we have 3 of them, okay? So we have components 1, 2, and 3. That's our k's, okay? Alpha is the mixture weight, all right? So the first component will have alpha k equal to 0.5, and then the third component has, alpha k equal to 0.2. And then p sub k is the probability density function. In our case, the PDF is the multivariate normal or multivariate Gaussian PDF, which is, has its own complicated thing, but it's, the probability of getting, your vector x given the theta components. Okay, the theta is all of the parameters of that multivariate Gaussian. So theta groups together. So the multivariate Gaussian requires a mu vector and sigma matrix, and theta k kind of gathers those together. So theta k represents the mean vector and the sigma matrix. Okay, so this represents both of those things. Okay, and then z sub k indicates kind of a 1, 0 indicator variable of whether x belongs to that mixture component or not. All right, so this is just kind of a mathematical representation of what we're doing, right? So this is how I can generate the mixture distribution in R, right? So here I've got alpha equal to my mixture proportions, 0.5, 0.3, 0.2. And then here I've got the mean vector and sigma matrix of component 1, mean vector and sigma matrix of component 2, mean vector and sigma matrix of component 3. And I'm going to gather all of the mean vectors into a list, and I'm going to gather all of the sigma matrices into a list as well. And then to generate, I'm going to use the library MVT norm, and I'm going to just create an empty matrix to store all of my values, right? So the first thing I'm going to do is I'm going to sample a value 1, 2, or 3 using this probability vector, right? So alpha represents my probability vector. I'm going to say, give me one random value of 1, 2, or 3 with these probabilities. So that will generate 1 with probability 0.5, 2 with probability 0.3, and 3 with probability 0.2. So I ask for those things. And then based on whatever k is, I'm going to generate a random value, one random multivariate normal value, okay? And because when RMV norm looks at this, it's going to pull out m means double bracket k. So when you do double bracket k, it's going to pull out the first mean vector. It's going to see the first mean vector has a length of 2, so it knows it's a 2-dimensional multivariate normal, right? So it's going to generate a multivariate normal coordinate using the mean and the sigma from group K, right? And so I will store those in my X matrix in row I. So here I'm saying I want 1,000 of these values. I'm going to store them in row I. And what we're storing is we're going to store the result of the random multivariate normal plus the component k. And so when I do this, this is what the resulting mixture looks like. If I label the dots, okay, if I label the dots with their colors, so we can see the black dots came from component 1. So if you remember, component 1 is centered at 0, 0 with variance matrix 9009, okay? That's gonna be all the black dots, this huge cloud here, okay? And then component 2 is centered at 4, 4 with variance 1.9.91. So there's high covariance here. It's centered at 4, 4. And then component 3, which is in green, is centered at -4, -4 with variance 2, -1, -1, 2. And that's what we see here, centered at -4, -4 with negative covariance. And then the second component is centered at 4, 4 with high positive covariance. Right? So this is the data with the labels, right? We know this because we generated the labels ourselves. Okay, usually they're unknown to us, and this is what the EM algorithm is going to try to do. It comes in with this unlabeled data, right? Remember, this is an unsupervised learning method. The data comes in like this, like a big cloud of points, and we ask, can you identify any structure in here? Can you identify? And so when we visualize this, we can say, you know, using our eyes, I say, look, try to look for like 3 clusters, and you might say, oh yeah, I kind of see, you know, there seems to be a cluster here. There seems kind of a cluster here, and therefore, you know, the rest has to be kind of its own cluster. And maybe we might be able to visualize this. And we're asking the computer also, can you kind of identify 3 clusters? We are not telling it any information other than try to identify 3 clusters, and the clusters are kind of multivariate Gaussian. All right, this what we don't want to do, well, no, we don't want to do. You could use k-means clustering, but k-means clustering won't do a good job because it's using Euclidean distance only, and it's using only that. With the EM algorithm as a mixture of multivariate Gaussians, we can take into account the variance, right? We can take into account that variance matrix. So let's say, yeah, we say certainly there's a center right here, okay? There's a point right here, okay? And let's say, yeah, there's a center right here. And so if we said there's a centroid right here at 0, 0 and a centroid at 4, 4, all right, and we know those are the answers. According to the k-means clustering algorithm, this point, say right here, this point right here is going to get classified as belonging to this cluster because the distance from here to here is very small, right? K-means cluster is looking at the nearest centroid. It's going to put this point right here versus the one in the center. And I think when we look at this, we can recognize that there's a high covariance, and that the points should definitely only belong kind of in this elliptical section here. There should only within this kind of highly elliptical section should we include any points, and this point right here should not belong to this cluster, right? Similarly, you know, this point over here will also get classified as belonging to this cluster, even because k-means algorithm is just using Euclidean distance. So this point right here, the distance to this centroid is not very high, and whereas the distance to this centroid is a little bit longer. And so using the nearest centroid, it's going to classify, you know, all of these points as belonging here. But I think visually we can, even without the points labeled, we can visually say, yeah, these points don't really belong to this cluster here. And so that's what we want to do. In the EM algorithm, we are not giving it labeled points. We're giving it completely unlabeled points, where we're asking, can you identify this? All right. So yeah, again, here's a question. Where should this point so we might say, yeah, okay, let's do that. But then here's a question: where does a point like this one right here, where does this point belong? Does it belong to this cluster? Does it belong to the center cluster? And even if we were to visualize this and take into account the variance covariance matrix and allow for covariances and things like that, we're still not quite sure whether this point right here, whether this should belong to the red cluster or the black cluster, right? So, and here, even if we look at the points with the answers, we wouldn't know that this point should have been black instead of red or something, right? They're kind of right in the middle, and there's an overlap between, these clusters. Same here, same as these points, right? There's a mix. These points down here are a mix of both green and black points, okay? And these points over here have a mix of both red and black points. You know, these ones are only red, and these ones are only going to be the black points. But this is a mix, and this is a mix. And so when we encounter a point like this, our algorithm will actually, what we want is an algorithm that not just says this is definitely red, and this one's definitely black, and this one's definitely green. We want to allow for a little bit of uncertainty here, all right? And so what we will do is we will use a probabilistic assignment. So rather than saying this point right here, which we're not quite sure if it should be red or black, rather than saying that point is for sure black or that point is for sure red, we're going to give it a probabilistic assignment. We're going to say maybe it's 60% black, 40% red, okay, and close to 0% green. So rather than strictly assigning a point to one cluster, like we did in k-means clustering, the way we're gonna assign it is we're gonna use a probabilistic assignment. And we use the Bayes classifier. So if you recall how the Bayes classifier works, we're gonna basically use the Bayes classifier to get a probabilistic assignment. And in the EM algorithm, this is known as a membership weight, all right? So each point will get its class assignments will be a probability vector, okay, that add up to 1. It's going to say 60% black, 40% red, 0% green, okay? Another point might be, I don't know, 80% green, 19% black, 1% red, or something like that, right? So you're going to get some kind of vector of probabilities that add up to 1. And so here is the interesting part that comes next is that once you have those membership weights, you are going to calculate the parameters of kind of each cluster distribution. So there, it's almost like so it's similar to k-means clustering mixed with Bayes classification. So in k-means clustering, you said this point belongs to this cluster, and this point over here belongs to this cluster. So you used you used strict assignments, and you said, we're going to assign each point to the nearest centroid. After you reassign the points, you recalculated the centroids. Okay. Here we're going to do something similar, except we're going to do probabilistic assignments, and we're going to calculate weighted parameters. So we're going to say this point is 80% cluster 1, 20% cluster 2, 0% cluster 3. And then when we calculate, what we're going to do now is we're going to recalculate the mean of this cluster, and we're going to say, we're going to look at that, and we're going to say, oh, it was 80%, this point will contribute 80% of itself to this cluster mean, all right? And we go through every single point, and we use a probabilistic mean or a weighted mean to calculate the mean. And same thing for the variance covariance matrix. We're going to estimate the variance covariance matrix using the membership weights of the points in each cluster. And that is, the estimates are done to maximize the likelihood of the values assigned to each cluster. And we're going to iterate back and forth between calculating the membership weights, which is the E step, the expectation step. We're asking, where do we expect this point to belong? And we're going to say, I expect it to be 80% cluster 1, 20% cluster 2. And we're going to recalculate the means and variances of each component, each distribution, to kind of maximize the resulting membership weights. And we keep going back and forth like that. And so you can think of this EM algorithm as a blend between the k-means clustering, where you're iterating back and forth between cluster assignments and centroid calculations, but also with the Bayes classifier. And with the Bayes classifier, we're doing probabilistic assignments of classifications. All right, let me give you your first quiz answer for today. The first quiz answer is C as in cat. C as in cat is your first quiz answer, so you can jot that down. C as in cat for your first quiz answer today. All right, so let's go into kind of how the EM algorithm will work and do the calculations. So the membership weights that we will calculate are done using the Bayes classifier. So we're going to be given the x values of the point, all right, that's stored in that vector x sub I. So given the values in x and the parameter values, the mean and sigma matrices of all the clusters that we have, which are all stored in this kind of entity theta, all right? So theta represents the storage of all of these things. It's not, don't think of it as a single matrix, but it's kind of just this parameter stores all of the information about the distributions. We're going to find this using the Bayes classifier. And so we're going to say, what's the probability that this point belongs to that cluster? And so z sub ik is equal to 1 when a point belongs to a cluster. So point I belongs to cluster K. So it'll be like the first point belongs to the first cluster. Okay, so z sub 1 is equal to 1 if the first point belongs to cluster 1. And then if the first point belongs to cluster 2, then z12 will equal 1. And if the first point belongs to cluster 3, then z13 is equal to 1. So it's basically asking, what's the probability that observation I belongs to cluster K? Okay, so zik equal to 1. What's the probability that observation I belongs to cluster K given the values in X, the values in observation I, and all of the other kind of parameters? All right, and we're going to use the Bayes classifier, which is going to be the likelihood multiplied by the prior divided by the marginal. The likelihood is just the PDF. The prior is given by this vector alpha sub k, and the marginal, like we've seen in the Bayes classifier, is going to be the sum of the numerators across all possible clusters. All right, and I hope that feels okay, because we talked about this already in the past. So we're going to calculate these membership weights, these weights of ik. And so alpha sub k is the prior probability from either the previous iteration, or if this is your first iteration, you're going to be given an alpha sub k, that a point belongs to cluster K. So it's going to be equal to basically the proportion of points that are assigned to cluster K divided by the total number of points. So if 30 points, if you have 100 points total and 30 points belong to cluster K or cluster 1, then your alpha sub K, or your alpha for cluster 1, is going to be 0.3. 30 out of 100 is 0.3, right? But one thing we have to note is that this n sub k, the number of points assigned to cluster K, is that it's not really the number of points assigned to cluster K. It's because, remember, we're doing probabilistic assignments. So, 0.1 could be 80% belonging to cluster 1 and 20% belonging to cluster 2. And 0.2 could be 20% belonging to cluster 1 and 30% belonging to cluster 2. And I don't know, 50% belonging to cluster 3. And so the total number of points assigned to cluster 1 would be the sum of, 0.8 plus 0.2 plus point whatever. You're adding up the probabilistic assignments. Okay, so that's what this is. It's the sum of the W sub I k's. All right, so we have a question that says, so this alpha doesn't have to do with the original alpha, or does it? So they are related, all right? So they are related in that when we generated the data, we said, I want 50% of my points to come from cluster 1, and 30% to come from cluster 2, and 20% to come from cluster 3, okay? So here, about, I don't know the exact count, but I'm expecting around 50% to come from cluster 1, 20% or 30% from cluster 2, and 20% from cluster 3. So I use that. And what I'm trying to do is I'm trying to recover that. Remember, the points come in completely unlabeled. So I have no idea. I have no idea what my original alpha is. And I'm trying to kind of recover that information. Okay, I don't know what the alpha is. So I'm trying to recover that using the EM algorithm. So I have to start off with some arbitrary point, right? And so probably in the beginning, I'm gonna say, well, maybe I think all three things have equal probability. I'm gonna say alpha is equal to 0.33 for each one. But, and then we go through, and then on the next iteration, I'm going to have, I'm gonna update my alpha. So alpha gets updated with every single iteration. So, a question came in that says, so we update alpha in each iteration, and the answer is yes. Okay. All right. We got another question that says, don't we need alpha sub k to get the assignments in the first place? So to get the probabilistic assignments? Yes. So in order to get the probabilistic assignments, alpha sub k is used. And so when you start, you just have to start off with some arbitrary starting location, right? Just like all of these iterative algorithms, you have to start somewhere, and that start somewhere could just be a random guess, all right? Just like when you do gradient descent, you have to start somewhere, and you say, well, where do I start? It doesn't matter. You just start somewhere and you go, and then you hope the algorithm gets you to where you want to go, right? Same thing with the EM algorithm. You know what you want label assignments, but you don't know where to start. So you just start somewhere, and then you let the algorithm run. That's kind of the point of these algorithms, is that you can start wherever, and as long as you follow the directions, it should at least get you in the right direction, okay? And so so probably a good idea to start in different multiple starting locations. And if all of the starting locations kind of still end up at the same ending location, then that's probably the answer, okay? Let me see. Okay, so I think on the first iteration we use those alphas. Question, so does this mean the initial weights have to be given to solve for the prior? Yeah, so you have to, you need some initial value for alpha sub k to get started. And then we update the alpha in each iteration. And yeah, W sub ik requires the alpha sub k, and it's going to be the alpha sub k from the previous iteration. Okay, so and if this is your very first iteration, you just have to give it some arbitrary alpha sub k. So it can be a random alpha sub k, or you could just pick the alpha sub k, and then, so that's the first iteration, and then after that, you just use the alpha sub k's from the previous iterations. And again, the alpha sub k's here are not technically the actual, there's no number of points that are assigned, because points are not actually assigned there. You get probabilistic assignments, and so it's not necessarily an integer. It's not an integer. It's the sum of the membership weights. It's the sum of the membership weights. Okay, so the difference between EM and the Bayes classifier we learned last week is that alphas are unknown here. The alphas, so there's the Bayes classifier is just like, what's the probability assignments, and the EM algorithm is that you're using the Bayes classifier in every iteration. Every iteration you update your probabilistic assignments using the Bayes classifier. And here the alpha sub k's, I don't want to say they're unknown. The priors are not unknown, they're just coming from the previous iteration. So you're using your previous information to get as your priors now. Okay, so this gets updated with every iteration. With every iteration, we update our alpha sub k's, okay? And when you update your, and the alpha sub k's are found by doing n sub k divided by n, where n sub k is the sum of your current membership weights. All right, the likelihood part, okay, so it's the prior, which is the alpha sub k, is the likelihood part is going to be the result of the PDF, okay? And so in our case, our PDF is the multivariate normal distribution, which is given by this mess, all right? And, you know, we did something like this when we did the Bayes classifier. We just used the multivariate normal density function in R, okay? And the DMV norm, again, and it's going to use our current estimates of the mean, mu sub k. Right now I have it called x bar k, but I guess mu sub k. And then the sigma matrix is variance sub k, right? And it's going to be different for each component k, because we've got, right now we have a mixture of 3 components, k equal to 1, k equal to 2, and k equal to 3. And we're going to use each of those as the mean and sigma values for each component here. All right, and so that's how we get the membership weights, okay? And then again, the marginal we find by summing up all the numerators, right? So you do the numerator, multiply for every single possible k, and once you do that, you can sum that up to get your marginal. And that's how you get your membership weights. Yeah, so for the first step, would we start with arbitrary x bar k and variance k? Yes. So for the first step, you just have an arbitrary starting location. You're going to have an arbitrary, you're going to say, here's my arbitrary starting location for component 1, arbitrary starting location for component 2, arbitrary starting location for component 3, and my arbitrary values for alpha sub k. You just start off with some arbitrary initial values, and then you let it run. And so I think in my slides I put in an example where we have, you know, some good starting values and some bad starting values, and we can see that they end up converging to different locations. All right, so once you have your membership weights, okay, which is kind of the cluster assignments. So if you think back to K-means algorithm, we iterate between cluster assignments and recalculating centroids. The EM algorithm is similar to that, except the cluster assignments are membership weights, and it involves using the Bayes classifier. It's a little bit more involved. So we're going to calculate the membership weights, and we're going to iterate between membership weights and recalculating the centroids, or in this case, it's going to be recalculating this mean value and the sigma matrix. Okay? And so the mean vector, or the mean value, is calculated by taking the weighted mean. So we're going to take each membership weight and multiply it by the x sub I, right? So we're going to take the current values of x, multiply it by its membership weight in class K, and sum those up, and divide by n sub k, where n sub k, again, is the sum of the membership weights. So this will be the weighted mean for class K. So we recalculate the quote centroid of each cluster according to the probabilistic weights of the points that have been, again, quote unquote, assigned to each cluster. So it's the sum of the weights multiplied by x sub I divided by n sub k, which is the number of points that belong to cluster K. But again, this n sub k is equal to this sum of the weights, right? And so this is just a weighted mean of all the points. And if we just pause to think about it, so points that are highly likely to belong to cluster K will have a membership weight that's close to 1, and will contribute pretty much its entire value to the value of the mean. Whereas points that are unlikely to belong to cluster K will have a W sub I sub K close to 0, and basically will not affect mu sub k at all, right? So if W sub ik is pretty much 0, it doesn't contribute anything or hardly affects the value of mu sub k. Okay, so more questions. If there are cluster 1 and cluster 2, we add both of them for one single value of the marginal. Yeah, so however many clusters you have to calculate the numerator for all possible clusters. So if you say, so just like the k-means algorithm, you have to specify how many clusters you're looking for or how many distributions you're looking for. And you have to take the numerator and you have to calculate it for each possible class or each possible cluster. And you calculate all of them, and then you sum all of them up together to get your marginal. So if you have 2 clusters, you're going to do them for both and add them together for your marginal. If you have 10 clusters, you have to calculate the numerator for all 10 clusters, and then you add them all together to get your marginal. So the algorithm does not tell you how many clusters you have. You have to specify that. So like the k-means algorithm, you have to specify how many clusters to look for. The problem of trying to figure out how many clusters to look for is a non-trivial task, and different people have tried to do research on saying, I don't even know how many clusters there are. Can you figure out how many clusters there are? And there's something called the Dirichlet process. The Dirichlet process will, you give it some kind of a hyperparameter that says it's more likely to produce lots of clusters or less likely to produce lots of clusters. So you just have one big knob that says more clusters or less clusters. And then from there, it will decide, okay, well, you told me more clusters. So, one run ended up with 97 clusters, and a different run ended up with 105 clusters, and a different run ended up with 80 clusters. Okay, and then another one, you crank that knob down and you say, it's more likely to have fewer clusters, and it goes through the process and it says, oh, I found 3 clusters. I found 4 clusters. Another run, I found 3 clusters. And that one, so the Dirichlet process will try to figure out how many clusters exist in a data set on its own. And you can look that up. It gets pretty messy. But there are algorithms that people have worked on to try to identify how many clusters there are without specifically saying how many clusters. But there's still another parameter that you have to specify, which says, I think there's going to be lots of clusters, or I don't think there's that many clusters. So it's really hard to say no information at all, figure it out all by itself, okay? So we find the weighted mean this way, and then we find the sigma matrix by weighting them as well. And so the sigma matrix for each component k is found by doing this. So we take basically how you calculate the variance. So if you remember, so if I deleted this W sub ik, this pretty much becomes the formula for the variance, right? So the variance matrix can be found using this. I guess the regular variance will be n minus 1, and then the maximum likelihood estimate for the variance will just be this. And here, I include a weight, the weight that observation I belongs to cluster K. All right, is this okay? I'm hoping that because we've learned the Bayes classifier and we learned k-means, that this thing feels like a neat, I don't know, combination of the two. All right, let's see it in action then, okay? So I intentionally did not show you the code here because that's your homework. So your homework this week is you kind of have to write this up, but we'll take a look here. So again, the data, this is unsupervised learning. And so the data come in completely unlabeled, and all we do is we just say, hey, we're going to look for 3 distributions here, okay? These are the true group assignments. And so I'm going to start off with some arbitrary mixing parameters. I'm going to just start off with say, let's do around even. So we're going to say 33% cluster 1, 33% cluster 2, 34% cluster 3. I'm starting off with some arbitrary starting locations for the means. We're going to start off with 0, 0, 9, 9, which is way up here, and -9, -9, which is way down here. And then for the covariance matrices, I'm just starting with the identity matrix, 1, 0, 0, 1. These are just arbitrary starting matrices. And again, you can start off with any other starting locations that you want. And these are just the initial starting values so that I can iterate through them. Okay, so if I plot the, I lost my words here. The kind of the contour lines of the, I guess the resulting multivariate normal distribution. So when you have the identity matrix as your covariance matrix, you know, if we took a profile, it would look like a normal distribution in the x direction. If you took a profile in the y direction, it would look like a normal distribution. But here it looks like this. It looks like circles because they have equal covariance, right? And then I colored these red and black and green. Now, the coloring is actually a lie, okay? Because all of these points are technically, they have probabilistic assignments. They are, so this, you know, points here will be like 99% cluster 1, you know, 0.1/2 of 1% cluster 2, 1/2 of 1% cluster 3, okay? And, you know, this point was probably 99% cluster 2 and maybe 1% cluster 1 and 0% cluster 3. Okay, but they're colored because you can only represent full colors here. I mean, I guess I could figure out some gradient way to do this. You know, these points on the border here are technically, these ones that are green are like 51% green, 49% black. And these ones over here that are on the border are probably something like 51% black, 49% green, okay? But I can't really represent the colors in this probabilistic fashion. So when I colored them, I just said the highest probability assignment, you know, color the point that. So because these ones were 51% green, they get colored green. These ones are 51% black, they get colored black. But there really actually are probabilistic assignments, all right? So the colors that you see here are just which class has the highest probability assignment, but it's not necessarily 100% belonging to cluster, to the green cluster. So I want to make sure that's clear. I don't know any other way to represent it, right? And I don't think our eyes would be doing a very good job of being able to distinguish some green to black gradient. That would be, I think would be really hard to see. So anyway, I just made the choice to color all of these points green and all of these points black, but they're not actually assigned to green or assigned to black. They're all probabilistic assignments of like 51% green, 52% green, 51% black, 52% black, something like that. Okay, so anyway, this is the very first iteration, starting off with the completely arbitrary assignments centered at 0, 0, centered at 9, 9, centered at -9, -9. And then what it's going to do is it's going to take all of these probabilistic assignments and it's going to say, all right, find the centroid or the weighted mean of all of these probabilistic assignments. Find the weighted mean of all of these red points according to probabilistic assignments. Find the weighted mean of all the black points according to probabilistic assignments. Also find the variance matrix, okay? And so right away, the next iteration, okay, so this is the text that basically says everything I said about the probabilistic assignments, okay? So right away, the next iteration it updates, okay? It updates and it says, okay, this is, after this, it says, okay, the centroid should get updated to around here and the centroid should get updated to around here. And based on the variances it calculated, these are kind of the ellipses that it has found. So just to make sure, these colorings were based on the WIKs. Yes, these are based on the membership weights. The membership weights, and I just said, whichever membership weight is the highest for that observation, color it according to that color. So if it said the green has the highest membership weight, it gets colored green, even if it's like a 51-49% split. Okay, so this is the center, and these are the updated updated centers and kind of variance matrices. And so you can see, because this thing had so much variance, when it estimated the variance of all the points, it blew up to be this huge thing. Okay, and then so we iterate again, and what it's going to do is it's going to say, okay, now that we've done this, let's redo kind of our probabilistic assignments and redo our probabilistic assignments. So what belongs to red, what belongs to green, and it updates the points like this. Okay, and so we can see this, and as I iterate, we end up recovering. So this keeps going. We end up recovering something pretty close to the original assignments. So iterating, updating, I don't know, it's just kind of fun looking at for me it's fun, I don't know about you guys, but updating the EM algorithm and the ellipses accordingly, it says, all right, these ones I believe to be green, these ones to be red. And again, these aren't all green, these just have the probabilistic assignment that is highest is green. But again, these are probably something like 60% green, 40% black, okay? And these ones are probably, you know, some probability red, some probability black, okay? And so these would be, after lots of iterations, these are kind of the final cluster assignments. Again, keeping in mind that these are probabilistic assignments, and they're just colored by the highest probabilities, not necessarily saying for sure these are green and for sure these are red, just probabilistically, highest probability red, highest probability green. And these were the original groups that generated, okay? And if you recall, the fact that this switched red and green doesn't matter because the labels are completely arbitrary and don't matter, right? But if you look at what points got colored, green or red, we see they are kind of close. It's just that, you know, in the true groups, this is truly a mix of the green and black points. And when we recovered the clusters, it's still going to be a mix of red and black, but these are all going to be higher probability red. None of these points will have a higher probability of being in the black group than the red group, but all of these points, even these points over here, will be some mix. These ones are probably, you know, 55% black, 45% red. Okay, these points over here, and that's kind of what we're seeing here. So this is the result of the probabilistic assignments, and not necessarily the thing. All right. So at the end, could you pick a final assignment for each point by randomly selecting from the final set of alpha k? You could, but that's generally not recommended. It's kind of like saying, could I randomly pick heads and tails for some sequence of things? And it's kind of a crapshoot in that, like, you don't know. When you randomly say, at the end, you say, okay, these are 50% red or black, and I'm going to just randomly assign them to red or black. You're probably not going to do that much better than the actual assignments. So probably not the best to just randomly pick them, because you're going to be off by some random amount. Okay. But if you don't do that, wouldn't the outliers for each cluster be lost? Yeah. So again, the point of EM algorithm is not necessarily the actual assignments. So it feels a little strange because that's what this graph represents, okay? And we're saying like, okay, this point is, you know, this percent red and this percent black and this percent green, and this point's this percent red and black and green and things like that. But I think more interesting, well, I don't know, is kind of the centroids or the means and the variance matrices. The actual assignments is just going to still be a probabilistic assignment. And I think that's fine. I think it's fine to leave the actual assignments as a probabilistic assignment. And you can say each of these points have a probabilistic assignment, because that's kind of what we end up doing. I know it's nice to say, all right, I've classified it as this, right? But it's often we can't achieve that. Let's see. Those are the true groups. All right, so here I intentionally picked some different starting locations. I started like here with different, again, so your starting locations are arbitrary, your starting sigma matrices are arbitrary, and your starting alpha probabilities are arbitrary. Here I chose the same alpha things and the same sigma matrices, but different starting locations for the mean, and then I let it just run, and it still it manages to recover pretty well. I guess I didn't do the one that failed. No. All right. But the answer is, depending on where you start, you can end up with results that don't converge to, quote, the true values, okay? But again, the answer is, the truth is here where I'm able to make comparisons between the true iterations or the true assignments and the final converged values, because I generated the values myself. But in real life, we don't really know. We don't really know the true assignments, okay? There's if you look up the EM algorithm, I think, on Wikipedia, I think they have one. All right, so here's a similar animation done for some data. This is Old Faithful data, and they just started off with some arbitrary locations, and they just allow it to converge. This is, again, a mixture of, there's no controls here, but you can see the initial starting values are totally way off, okay? And then they just allow it to run. So it's a similar animation to, I don't know what's going on here. Similar animation to what I've produced, but I guess they colored them using the Old Faithful data and stuff here. Question, would you use the EM algorithm instead of k-means? Where would you use the EM algorithm instead of the k-means? So let's go back to the Wikipedia page. So here's an example. I think this is what I put in your homework. Something based on this, okay? So, oops. Oh, what just happened here? All right, so here you have these things that look like Mickey Mouse ears, okay? And so the original data has, you know, clearly different amounts of variance here. And k-means can't account for that. K-means just says, let's look at Euclidean distance. So these points that are here, right? These points here are closer to this centroid than they are to the centroid in the middle. And so they're going to get assigned to blue, okay? So k-means clustering doesn't do great on data like this, right? And the EM algorithm does a lot better because it says, hey, you know what? This middle cluster here has some huge variance. So let's just go with that. These points, these middle points this middle cluster has huge variance. So we allow for that. Whereas these groups up here have less variance, and it accounts for that as well. K-means clustering only says Euclidean distance, which just takes a difference and it says, oh, this distance is bigger, therefore it can't be in that cluster. And so you get kind of suboptimal performance. And I think this is kind of the example I have you guys work through in your homework. and you'll compare the results of k-means clustering to the EM algorithm. So if you suspect, so I guess to answer your original question, when do we use the EM algorithm k-means? If you suspect it's possible that your groups have different amounts of variance, then the EM algorithm will be a better choice. K-means is going to be a simpler algorithm if you believe all of the groups have the same amount of variance. If you think like all the groups have the same amount of variance and you kind of know how many clusters to search for, you can run that. Whereas the EM algorithm would allow for different amounts of variances. There. In practice, are these algorithms actually used to identify objects in an image? No, I would say these are not used for image recognition. So pretty much all image recognition algorithms are going to be neural networks. Whereas the EM algorithm will be used to identify structure in, I don't know, more quote unquote simpler data sets of where you kind of have a well-defined number of variables. So things like the iris data set, you can use the EM algorithm where you can say, search for 3 clusters of species based on their thing, and it will probably recover the mean and variance of your Virginica, Setosa, versicolor species. The EM algorithm will be used, where you have kind of a certain number of numeric variables and you're looking for kind of structure in there. And again, it's best suited if this specific one where we're looking at a mixture of Gaussians, you got to use it when it is reasonable to believe that your data is multivariate normal distribution and not some other crazy distribution. So all of this requires a little bit of knowledge of the underlying data, and you can ask, well, is it reasonable to believe that this thing is a mixture of normal distributions, right? So here we're looking at old faithful eruption data in this diagram, right? And so they looked at how long so Old Faithful is the geyser in Yellowstone, and we can't quite predict how often the geyser will erupt, okay? And when it erupts, sometimes it lasts for a short amount of time, sometimes it lasts for a long amount of time. And then how long do you have to wait between one eruption and another eruption? Sometimes you have to wait a little, sometimes you have to wait a lot. And they plotted the delay between eruptions and the duration between eruptions. And it looks like there's kind of a couple clusters here. And so they ran the EM algorithm to kind of identify the center of each of these clusters. Does that mean anything? I don't know. I don't know what a geologist would say about the meaning of these eruptions and what kind of process is happening in the planetary science. But there might be something like this, okay? And so is it reasonable to assume that these variables have some kind of multivariate normal distribution? Maybe not, I don't know. So so that's what we have. All right, why don't we, let me give you your second quiz answer. Second quiz answer today is D as in dog. D as in dog is your second quiz answer. And then why don't we take a 5-minute break, and then I'll go ahead and I'll get started on PCA. And then we'll end for the day, and then we'll, I guess that'll be it. Okay, so I'll get started on PCA after the break. Second quiz answer is D. We'll go ahead and take 5 minutes here. Okay, well, I don't know. Do you guys have any questions before I go on regarding the EM algorithm or something? Daniel asks, is this useful for trying to categorize effects? Like for the Old Faithful set, say you want a large or small eruption category. Yeah, I mean, so what you're looking for, again, this is an unsupervised technique like clustering in that you're trying to kind of group observations, similar observations together. And this time we can group observations that are similar together, even though there might be a different amount of variance between them. Right? So as far as kind of unsupervised techniques, we have regular old k-means clustering, and that just groups observations together by looking at Euclidean distance. And then we looked at the kernelized k-means clustering, which allows for grouping observations together with kind of different non-linear I don't know, boundary isn't quite right the word, but just kind of that are separated by kind of in a non-linear sense by projecting the data into higher dimensions. And here with the EM algorithm, we're able to kind of group together observations that are similar despite having different amounts of variance between them. And so these are all kind of unsupervised in terms of grouping the observations together. The one major limitation with all of these methods is that they are very much designed for numeric variables. So I haven't really talked about clustering data together if you have categorical data, which is a common problem that people encounter in the real world, and going from categorical to numeric variables. So almost all the techniques that we've developed as far as clustering goes deal with numeric variables. In fact, if one of the most popular kind of machine learning packages out there is for Python, and that's scikit-learn, okay? And if you go to scikit-learn, they will say, hey, these are kind of the different things that we have. We have classification algorithms. So this is a supervised learning method where you have already labeled what the target values are, right? So classification, you already know what class the training data belongs to, and then you have new data and you're trying to do that, right? Regression is a supervised learning method in that you know the value that you want, and it's a numeric value, and you're trying to predict that numeric value. But clustering would be the unsupervised learning, okay? And as far as unsupervised learning, everything for clustering, so you have k-means, you have Gaussian mixtures, which will be your EM algorithm, you have all of these other things going on too. They will be, they're all for numeric variables. All of these things are for numeric variables. And so if you have a categorical variable, then it falls under this group of pre-processing, feature extraction, and you're trying to convert your categorical variable into something numeric. Okay, in fact, scikit-learn requires all of your data to be in a matrix, basically in a numeric matrix. And so that's kind of where we are right now in the state of machine learning, is that everything has to be numeric. Everything is a matrix, and we're going off of that. So you could probably have an entire another course on pre-processing and feature extraction and feature identification and feature engineering in terms of going from categorical variables into numeric variables. And then once you have it in numeric variables, then you can feed it through one of these machine learning algorithms. Now, can we do machine learning straight on categorical variables? I think some people are trying to work on that with moderate amounts of success, and there's probably a lot of open-ended questions there. Are the PCA slides posted? I have not posted them. Let me post them. I guess the question is, so this is what I'll do. Let me get rid of the week 5 Wednesday viewing lecture, because we'll get rid of that. All right, so week 6 Wednesday, we'll get rid of that one. And then I will unhide the homework 6. And I guess this will be the draft version, just so you can follow along. And then Probably I'll relabel it to lecture 5-2 part 2 or something for PCA. All right, so we are going to talk principal components analysis, all right? And PCA falls under, as far as kind of machine learning goes, falls under dimension reduction, okay? Dimension reduction. And there's a bunch of different dimension reduction things, but the kind of the most popular choice would be PCA, principal components analysis. And there's a whole bunch of, I don't know, stuff. That's scary looking. What is this? These faces, oh geez. Eigen faces, oh, what is that? Okay. I'm sure it's something. Okay, but anyway, with principal components analysis, we are, its most common application is dimension reduction, right? And so the idea is you got a data set with lots of variables, and the variables in the data set are likely to be correlated, possibly correlated. And what PCA will do is it transforms the data into uncorrelated variables, all right? Now, why would we want to do this? Well, the goal is often dimension reduction, right? And if we can take advantage of the fact that many variables are correlated, can we reduce the number of variables and still capture or convey the variation that exists in the data, right? And the reason why do we even want to reduce the number of dimensions, okay? Okay, because whenever you reduce the number of dimensions, you are losing information, okay? You're losing information whenever you reduce dimensions. But our brains have an easier time thinking about fewer variables, right? We have an easier time thinking about lower dimensional data, okay? First of all, we can, as far as visualize, we can really only visualize data in 2 dimensions and 3 dimensions. I guess 1, 2, or 3 dimensions. It's difficult to visualize data in 4 dimensions, right? Like if you look at a tesseract, which is basically a cube that exists in 4 dimensions, this is the animation. It's a 4-dimensional thing, and this is the shadow of a 4-dimensional object in 3D, okay? This is a shadow of a 4-dimensional object in 3D, and it is constantly morphing like this, and it blows our mind. Like we can't, it's hard to, this represents a tesseract, a 4-dimensional cube, okay? This thing also represents a 4-dimensional cube. This represents a 4-dimensional cube, and it's the idea of projecting this higher dimensional thing down into 3D. And so it's hard for our brains to comprehend, you know, what is this? What is this? Does that make sense? Like, I guess if you think about it long enough, maybe you can make sense of it, but it's not as intuitive. It's not as intuitive because we can visual. So anyway, if you can get something down into 2D or 3D, we can make a plot, and we love that, right? We can visualize it and it looks great. If you, also, it's just easier, right? The whole reason, okay, why do you guys have a GPA, right? You guys are, I don't know how obsessed students are with their GPAs. I always tell you, don't be obsessed with your GPA. But what GPA is, it's dimension reduction, okay? Where your life, okay, well, is much more than your GPA, but okay. Even your academic career, all of your work at UCLA, all of that, is the result of a whole bunch of different classes and different things like which professor you had and what, you know, the curve and whatever. There's all sorts of things that factor into that thing. But, you know, when you apply to grad school, they have to make a quick decision, and they don't want to know your whole life story in terms of like what happened in college and why did you get this grade or this grade, you know. Can they just reduce it down to one single number? Okay, and that's what the GPA tries to do. It tries to just reduce everything down to one single number, and they say, this number, 3.85, this represents your academic performance in school. And it's very reductive. You lose a lot of information. Is it useful? It's useful in terms of making quick comparisons. It can be useful, okay? Is it a good method? I don't know if it's a good method, okay? But it's easier to think about something in fewer numbers of dimensions than something much more complicated, okay? So here's an example, right? And if you have to go shopping for a house or looking for an apartment or something, and you say, well, how much should I pay for the house, or how much should I pay for rent on this apartment? There's a whole bunch of factors to consider. One is like, and if you look at a housing data set, it's going to have a whole bunch of variables. It's going to say like livable square footage, total square footage, including the basement, the number of bedrooms, the number of bathrooms, the size of the lot. There's going to be other things like, is there a pool? What's the roof style? What's the air conditioner? Is it central heating or ductless or whatever? Is there a garage, and how many parking spaces? When was the thing built? What's the quality of the kitchen? What's the quality of the floors? All of this kind of stuff. Oh, also like, what's the location and zip code? What are the ratings, local school ratings? I think I had like more things on here that just didn't fit. You know, like what's the crime rate? What's the median price of the houses that are nearby? All sorts of stuff, right? And I argue that all of those variables, and there might be like 80 or 90 of them, can be reduced probably down into 3 overarching categories. One is, how big is the place, the size, okay? Basically, because the number of bedrooms, number of bathrooms, square footage, those are all going to be highly correlated. They go up or down together. The amenities, okay, and quality of the place. So if generally, if the place has a really nice kitchen, it will generally have nice floors and a nice bathroom as well. If the kitchen, you know, if a place is advertised as a fixer-upper, it means the kitchen's falling apart, the floors are falling apart, the bathroom's falling apart, and it's going to need some work and things like that, right? And so those will change it, the price. And then the quality of the neighborhood, right? Is this a nice neighborhood where people want to live? Is this kind of a neighborhood that's not so nice? Those are kind of the neighborhood desirability would be the kind of a third variable there, right? You know, if you're in California, basically all the neighborhoods in California have high desirability, and you know, compared to other parts in the nation, in that, you know, it's a lot more expensive to live in California versus say Nebraska or something like that. Okay. And oh, nothing against Nebraska. Nebraska is a beautiful state. Just there's not as much demand for homes in Nebraska, right? And so you can buy a huge house in Nebraska for the size of a studio apartment in California and things like that. So, you know, trying to find a place in Westwood, it's so expensive, right? It's so expensive because it's right next to UCLA, which is a highly desirable quality for all the students, right? And that keeps the prices very high, right? So dimension reduction is very useful in that it makes it easier to think about. And so these are just examples. I did the GPA, your SAT, GRE. It takes something complicated like intelligence or mathematical ability, and it reduces it down to just a couple of numbers, right? You get a math score, verbal score, writing score, and I guess that's a higher dimension, right? You get 3 dimensions, but again, it's reducing something, a complex thing of, what is this? It's trying to measure something, okay? And I hesitate to use the word intelligence here because it's not necessarily that, but it reduces it down to 3 numbers, right? There's other things like your credit score. When you apply for a loan, all of your financial background is reduced to a single number, and they try to decide whether you get the loan or not based on that, right? And so when you apply a loan, there's usually just 2 things that they ask about. What's your credit score? They ask for your social security number so they can look up your credit score, and then they ask for your annual income. How much money do you make, right? And so if you make a lot of money and you have good credit, sure, you can probably get any loan you want. If you don't have good credit, they're less likely to do that. Or if you don't make a lot of money, they're less likely to give you a big loan. Things like that, right? In the NFL, okay, when a quarterback plays, he gets a passer rating, right? It takes down the entire performance in a game, and it gives back a single number. And it's going to be kind of a result of like how many passes the quarterback attempted, how many passes they completed, how many touchdowns they made, how many interceptions they threw, which was a bad thing. That just gets factored down. Or, you know, in track and field events, there's like the heptathlon and the decathlon. You know, the athletes in heptathlon, which is a, you know, women's Olympic event, the athletes compete in 7 events, right? They run around, they do the hurdles, they throw the javelin, throw the shot put, they jump over, they do high jump and long jump and stuff like that. And but they have to be ranked from you know, gold, silver, bronze to last place and stuff like that. So they have to reduce the performance in 7 different events down to a single score in order to award a gold medal. You can't, you know, if you just treated them as 7 separate events, you can't have like, oh, you were the winner of the hurdles, but this person was the winner of the long jump, so you get, so each of you get 1/7 of a gold medal or something. It doesn't quite work that way, right? So we have to you know, in these cases, reducing the number of dimensions is useful. So one way we can think of this, one way we can think of dimension reduction is by the analogy of casting a shadow, okay? And so I don't know if, can I do this? Does this work? All right, so here I got a piece of paper here, and is there a shadow? Am I casting, is my hand casting a shadow? Not really, kind of. Okay, well, the idea is in life, we exist as 3-dimensional, like everything we interact with exists in 3 dimensions, right? Even a piece of paper has a 3rd dimension, right? But when we cast a shadow, that shadow exists only in 2 dimensions. Okay, oh, you know, I get it. I get a better shadow here, right? Okay, so here my hand is casting a shadow onto the wall, right? And that shadow looks like a hand, okay? But if I turn my hand like this, okay, it's still the same object, but if I turn it like this, it's a little bit harder to tell what this shadow is, right? If you looked at this, if you only saw this, you might not know that it's a hand, right? If you see this, it's very clearly a hand. If you turn it like this, it's not as clear that it's a hand, okay? And so what we want when we do PCA is we want to find a lower dimensional representation, right? So this is a lower dimensional representation. This is a 2-dimensional representation of a 3-dimensional object, okay? This is still, it's a 2-dimensional representation of a 3-dimensional object. And that's kind of what we're doing with PCA. We have a high dimensional object, and we're going to create a, quote, projection of it in lower dimensions. And what we want is we want to pick a projection that maintains as much of the structure of the original object as possible. So we want the resulting projection, in the case of our hand, we want the shadow to look like a hand, so that when you see the shadow, the 2-dimensional representation, you can say, oh yeah, that's a hand. Whereas if you pick something else, right? If you pick the thing where it's not quite clear, then that's not a good representation. Okay, so that's kind of what we're doing. So you can have some high dimensional data, and the idea is we want to project it down to a lower number of dimensions that maintain as much of the structure as possible. Okay, and so depending on how the shadow is projected, the shadow may resemble the object or it might not. And so, you know, when you pick a lower dimensional projection, you want something that resembles the original data. So mathematically, when we say we want a lower dimensional projection that resembles the original data, we're saying we want a projection that captures as much of the variance that exists in the original high dimensional data. okay? So if we reduce the dimensionality of the data, whenever you do that, you're going to lose some of the variance, right? You can't capture all of the variance, right? So even this shadow that looks like a hand, it doesn't capture like the exact depth, you know, like you're still losing some information there, okay? But you want to kind of, you still want something that has a high amount of variance. So we're gonna, so what we're gonna do is we're gonna search for a lower dimensional projection that maximizes the variance in the resulting projected space. All right, so this is how we're gonna do it, okay? The original data exists in m dimensions, okay? So that's our high dimensions. M is m dimensions. And then the nth observation in the original data will be y sub n. I don't know what's going on with my dog here. Give me a second. Okay. So our nth observation exists in m dimensions, okay? And this is going to be it, all right? And what we want to do is we want to project this m dimensional data down to d dimensions, okay? Where d is a number less than m, okay? And so after projecting the nth observation down to d, we're going to call the result x, okay? The nth observation will be x sub n, and it's going to be, the vector will be x sub n from 1 through d, okay? And so what PCA is going to do is it's going to define d different vectors, okay? Each of those vectors will be w, okay? W sub d. Each vector will be m dimensional, okay? And what it is that when you project your nth observation in y down to x, what you're doing is you're going to multiply y times this length m vector w sub d, okay? And so you can think of w as kind of like a recipe for how to combine the elements of y. So the values in x sub n d, so the nth observation in x is going to be a linear combination of the values in y. So if you have, so basically, if y exists in 3 dimensions, maybe I should just use numbers, right? So let's say y is 3-dimensional data, and we want to project down to 2 dimensions, okay? We are going to define 2 vectors of w. We're going to define w1 and w2, okay? And each of those w's, w1 will be a vector of length 3, all right? And we're going to multiply w, which is a vector of length 3, times y, which is a vector of length 3, right? And when you do the matrix multiplication, they add up to one value. You multiply the 3 elements together, element-wise, and you add them together. And so, and that w, the w length 3 vector w is basically like take the first dimension and multiply by this weight, take the second dimension, multiply by this weight, and the third dimension and multiply by this weight, and you combine them. And it's just a linear combination of the values in y for how you should combine them. Okay. What are the internal values of w's? They're going to just be w's that that the PCA results in. Okay. So for example, if let's say the values of w are 1, 1, 0. Okay. Basically, and let's say y, your vector y is, you know, data in x, y, z, right? I don't know. Maybe that's x1, x2, x3. And if you have 1, 1, 0 for w, it basically just means the way we're going to project project it down is we're going to keep x1 and x2, throw away x3, and then we just add x1 and x2 together. Okay, so it's just a linear combination of the values in y. Okay, so the internal values in w, it doesn't matter. They're just arbitrary weights. They're just arbitrary weights that says for the first component d, for, you know, when we project down to 2 dimensions, we're going to have 2 of these W vectors. So for the first one, it's going to say combine the values of Y in this way. And then for the second one, it says combine the values in this way. Okay. And then, oh, I did the example I listed out, but you just kind of multiply your W's times your Y's and you get basically your coordinates in X. And so what we want to do is we want to choose our vector W so that the variance in the resulting projected space. So we want it so that when we multiply Y times W, the X, the resulting X, the resulting data has maximum variance, okay? So the first vector, W1, will be the set of weights so that the variance in the projected values, which it will be the X sub 1, will be as high as possible, okay? And then the second vector will also maximize the variance in the second dimension, X sub n2 and stuff, but the requirement is that the vectors W1 and W2 are orthogonal. And what that means is that they're gonna be uncorrelated, that when you kind of project them against each other, okay, that they are orthogonal, which basically means they form a right angle if it's 2-dimensional data, but in higher dimensions, it's kind of the whatever, the equivalent of that. They're orthogonal, right? And so on. The third vector will maximize the variance in the third direction, but will be orthogonal to all of the previous other vectors. And so that just means, oh, this is a typo, that Wi transpose Wj, I gotta find that. Wi transpose Wj is equal to 0 for all I that is not equal to j, okay? And to avoid having infinitely many solutions, right, we're gonna restrict the length of each vector W to be 1, okay? So we're gonna set, you know, W transpose W has to equal 1. So basically the norm of the norm squared, or the Euclidean distance, the sum of the squares has to be 1. Is this all right? Oh, I'm going to run out of time. But I was kind of anticipating that. Okay, so what we're going to do is we're going to derive the vector W1 so that the variance in the resulting projection is maximized, right? And then, and to make our life easier, we're going to center our original data, okay? So we're going to subtract the column mean from each column, and that's going to center our data, so that y bar is equal, the y bar is equal to the 0 vector, so that the sum of the y's over n is equal to 0. Okay, so this is what it means to center our data, is that this thing, the sum of y over n is 0. So let's just work with one weight vector W, and we're going to just project it down to one scalar value x of n. Okay, and so our weight vector has length m, because we're going from m dimensions down to d dimensions, and now d is just 1. Okay, so we're going to go from m dimensions down to just 1 dimension. We're going to take our weight vector W, multiply it by y sub n, and that's going to produce our x of n value. So we're projecting from m dimensions down to 1 dimension. And what we want is we want the variance of this projected data to be maximized. Okay, so the variance of this projected data, x of n, is going to just be basically this. Okay, x of n minus x bar squared, 1 over n. Okay, this is the population variance. Okay, if we wanted the sample variance, it would be 1 over n minus 1. It doesn't matter. Okay, honestly, like we would arrive at the same conclusion. But here I got 1 over n. So this is our sigma squared here. Population variance. Okay, so if you recall, we said that y bar is equal to 0, which means the sum of the y's, we've centered our data so that the sum of the y's over n is equal to 0. So we can say that the mean of x bar is also 0, because the mean of, if we think of, well, what is x of n? X of n is the result of multiplying w times y, right? So we've defined x as the product of w and y. So when we multiply w and y, this is what we have. And so the sum of the x is over 1 over n is equal to this, we can extract the w, and we got w transpose times the sum of the y's over n. And this thing is equal to 0, which is y bar. This is the definition of y bar. And so w transpose y bar is going to equal 0. So we know that the mean of x is 0. The mean of y is 0. When we multiply that, when we multiply y times w, the resulting x will also have a mean of 0. Okay, so I can take my variance and I can go through some math, and I'm going to get this thing. Okay, so if I'll go through this quickly. Okay, so I know my mean of x bar is 0. So now I get the sum of 1 over n times the sum of xn minus 0 squared. Okay, so this becomes xn is defined as w transpose y. And so now I've got the w transpose y quantity squared, which when you multiply it out becomes w transpose y times y transpose w. And the w's are not affected by the subscript n, so I can extract them out of the summation. Okay, and so now I have w transpose times the sum of yn transpose times w. Okay, and the dimensions work out just fine. Okay, and this is what we have here. Okay, so I've got, if you recall, the covariance matrix. Okay, the covariance matrix is defined as this, right? Y minus y bar transpose, and y bar is equal to 0. So I can simplify my covariance matrix because the y bars are equal to 0 to just 1 over this. And therefore, my variance of x is given by w transpose times the covariance matrix, which is this thing, times w. Okay, so my sigma squared, my variance of x is w transpose covariance matrix times w. Okay, and so you can see it doesn't really matter if I used n or n minus 1 here. All right, so what I want to do is I want to maximize this. I want to find the w's that are going to maximize the variance here, right? And now if I just wanted to maximize this, I would just pick the biggest w's I could possibly pick. But we have the constraint where the sum of the w's have to be 1. Okay, so I've got, so I'm going to maximize this quantity. I want to maximize the variance subject to this constraint. So the way we do maximization subject to a constraint is using a Lagrange multiplier. And so, so we've got w transpose CW minus lambda times w transpose w minus 1. Okay, I'll take the derivative of this with respect to w and set it equal to 0. So when I do this, this becomes 2 matrix C times w. And when I take the derivative of this, I get 2 lambda w. The derivative of the minus 1 is equal to 0. So I got 2cw minus 2 lambda w is equal to 0. And solving for w, now I got cw is equal to lambda w. And so I don't know if this looks familiar. I've got a matrix C times a vector w is equal to a scalar value lambda times the vector w. So yes, so this is in the form of solving for an eigenvector. All right, so sorry, I'm going a couple minutes over here. So when you have a matrix times a vector is equal to a scalar times a vector, we say that this vector is an eigenvector of this matrix, and this scalar is an eigenvalue, is the corresponding eigenvalue. So we want to find a solution for this. So we have matrix times vector equal to scalar times vector, and the solution is W is an eigenvector of C, and lambda is the eigenvalue. Okay, and so basically, to maximize the variance of your projected data, you are going to pick your vectors W, the weight matrices that you're going to multiply by Y, to be eigenvectors of the covariance matrix of the centered data. All right, so in summary, what we're going to do is we're going to center our data so that the column means are 0. Then we're going to compute the covariance matrix C, and then we're going to find the different eigenvalue eigenvector pairs of the covariance matrix. Okay, and then we select the eigenvectors with the highest eigenvalues, and we keep those. And so x will be the result of multiplying y times the resulting w eigenvectors that we've selected. All right, I will go ahead and post homework 6, which covers PCA, and it kind of acts almost like a tutorial for projecting some data from higher dimensions down to lower dimensions. And so I'll let you guys work through that. And that will be it. So again, is there an R function for finding the eigenvector? Yeah, it's called eigen. You just type in, so you can do eigen. Oh, last quiz answer. Last quiz answer is A. A as an apple. A as an apple is the last quiz answer. Okay. And so, yeah, if you call eigen, it will do the find the eigenvalues and eigenvectors, or we call that the spectral decomposition of the matrix. Okay. Requires a square matrix. Okay, so so that will be it. Okay, so I'll post homework 6. And so I will lecture on Monday. You don't have to come. It's your day off. And then we won't have class on Wednesday. And you have until Thursday to watch Monday's lecture. And the final exam will be on Friday. So make sure you watch Monday's lecture. I will go over the topics for the final exam as well in Monday's lecture. All right, have a good weekend, you guys, and we'll see you then. See you, I guess, whenever. I don't know when I'll see you next. So at least definitely for the final in a week from Friday. All right, I'll see ya.